Today we're going to cover Networking Basics, Chapter 5, OSI Data Link Layer, and Ethernet. So as you can see here, we have the OSI layers and the TCP IP model. As a review, the OSI model is for teaching. It's got 7 layers, more detailed. The TCP IP model was made for the internet, so it's more broad. In each of the sections, there's only 4. The top 3 layers, 7, 6, and 5, which match up to the application layer in the TCP model, provides the user the interface, so the application they're using. The transport layer breaks things into segments and manages the communications. And the network layer, which matches up with the internet, organizes data for transfer. And we call those packets. And then we hit the data link. We're also going to be a common exchange over the media. So independent data can go across any type of media. That's the big thing about the data link. So there's 2 basic functions of the data link layer. The first function is preparing the 1s and 0s to go up to the upper layers, which turns it into a frame, passes it to the network layer, which would be a packet. And also the very first function is to get the data off the wire, which would be 1s and 0s, turn it into a frame, then pass it on to the network layer, etc. So here we see we have independent media here. So we have a frame. We call it the PDU, the packet data unit, is the frame at layer 2. So no matter what device you're using, you're going to be using a frame. So you can see here we're using, whether it's a computer, tablet, phone, they all have a frame and data link component to it. If we go to the media, they're all independent. You can go through copper, fiber, wireless, satellite. And also the network has more than one device on it. You're going to use a common media, whether it's going to be the copper, fiber, or the wireless. So the data link layer is very important to accessing data from the media and going up to the upper layers. So supporting the upper layers. So we have a PC router, then it goes into the WAN over, looks like satellite. So different protocols for different media. So if we look at how the protocol governs the format, so depending on if you're coming from a NIC card onto a copper wire going into a switch, as we have here, it turns it into a frame. It de-encapsulates the packet coming from the network layer, constructs it into the frame, and then forwards it out with all the addressing and the rules that govern that. But once we go past the router into another media, the frame possibly will change. In this case, it did change. So the rules in the framing and the addressing has to be made for that particular protocol. Once again, we go all the way through, and it's going to go through the different medias, different protocols, different formats, different addressing if it needs to, and once again, coming through the wireless. So we have all these independent data going across different types of media with their protocol rules and their addressing schemes. So how do we control the access of the media? So layer 2 will encapsulate a packet into a frame and get it down to the wire. So the method's called the media access control. And there's a couple different things that we do at the media access control. So if you have a LAN, your media access control is going to be slightly different than if you were on the WAN. So there's a component for the LAN and the WAN. Just remember that for future reference. So how do we control the local media access? So 2 computers connected through copper, Ethernet, going into a router, going across a serial. So from the network layer, it's a packet. We know that the header is going to be the IP address. So now when we go to the LAN, we're going to add another header and a trailer of the LAN, which would be the MAC address. Once it moves across a serial, the WAN header goes in, which is still a data link WAN header. So there's a little bit different rules or addressing. It's going to change there and go across the WAN. So different media, different characteristics, different ways to access the media, depending on the device you're going through and the protocol they're using. So the protocol can control the device and determines the media access control. So creating a frame. So we have a packet coming from network layer, coming down to the data link layer, and we're going to add a header to it. And this header is going to be able to let nodes communicate with each other. It's going to allow the individual nodes begin to send data and end. If any errors occur, they'll be detected, but they won't be corrected. And then you're going to wait for the next node to be ready to communicate to the physical wire. So creating the frame, so like last chapter, it's a review. It's a bit pattern at the start, and it's a bit pattern at the end. So that bit pattern determines the start and the end of the frame. So there you see the bit pattern, and then all the other things, the frame addressing, and also the error correction, error detection, and then the stop frame. So data link, NIC cards, physical address, MAC address. So we're going to talk much more about those, but it's a hardware and a software component. So at the data link layer, you have both. So if you look at the implementation of the hardware, it's going to be at the physical data link, and then the software starts at the data link and moves up. So if you look at the other layers, they're all software dependent, where the data link is also implemented in hardware. So here's the standards that define the data link layer, the ISO with some HDLC, IEEE. Remember the 802.3 Ethernet and 802.11 right now. Those are your two important ones. And then the other ones are not so much important. So the IEEE has a sublayer of an LLC and a sublayer of the MAC. So the two functions of the MAC address are to get the ones and zeros off the wire or the medium, and then get it to a frame format to pass it on to the upper layers so the network layer can read it, transport layer can read it, and then ultimately the user will see the data. So placing data on the media, we have to regulate that, so we just can't throw data on the wire all at one time. So in this example, there's no control, and the users just send data, and it's going to create collisions, and we'll show this later in a demo on Packet Tracer. So if we just take turns, we have to have rules for taking turns. Who goes first? How long do you get to go? All those rules that govern how you access the media and how long you get to keep it. So media sharing, if the nodes need to share, there's got to be rules in place, or you're going to have the collisions that occurred in the early networking. And the topology determines how it appears in a data link. So we'll talk more about topology. Remember, we had the physical and the logical. This is more of the physical topology. This is the physical topology. So two basic methods for shared media is we need rules. So how do we start the rules for sending data to the actual medium? Controlled access. Only one station can transmit at a time. Devices wishing to transmit must wait their turn. No collisions. And some deterministic networks use token passing. And we'll demonstrate that token passing in just a minute here. So the two ways to access the media are carrier sense multi-access collision detection for Ethernet and carrier sense multi-access collision avoidance for 802.11. We'll get in more detail on those later. That controls the rules for accessing either Ethernet or accessing wireless. So point-to-point connections, there's only one way to send it. There's only one receiver. So it's a one-to-one connection. So you can either have full duplex, which means you can send and receive at the same time, or you will have half duplex, where one device must hold until the other device completely sends the transmission. So we both have a physical topology and a logical topology, and the physical is how the nodes arrange on the physical connections. And the logical will be more of a point-to-point or a multi-access or a ring. And that determines how the frames are transmitted amongst the computers or end devices. So a point-to-point logical topology is we have two routers. They're sending their WAN frame into the cloud. So it really doesn't matter what devices are in that cloud. They'll determine if the frame is going to stay the same or change according to the different device or the protocols those devices must use. So multi-access logical topology enables a number of nodes to communicate using the same media. So what we have here is a bus topology. So if A wants to send to E, it checks for transmissions. Media is available. Transmit. First node sees it. The ones that don't need it, it's not addressed to them, they'll drop it. And so what this is it's not a very productive, efficient network when you have to have every host see every transmission from every other host. We call that broadcasting. So check for other transmissions after you receive, then if the media is not available, you must wait, and then you can transmit. This is a ring logical topology, so if A wants to send a D, it's going to go host by host. Each host will determine whether it's addressed to that host, and it will either drop it or pick it up. In this case, no. C doesn't need it, not for me. Now D is addressed to it, it is for me, so yes, I'll pick that up from the data, from the wire, media access control to the LLC, prepare it to a frame, and then pass it on to the layer 3 for network, which would be a packet. So end addressing for data link. So there are many different layers and protocols. So the data link will describe the feature required to transmit the frames. So it's going to be media independent. So whether it's copper, fiber, wireless, cell phone towers, or satellite. So no single frame protocol is designed for all those different types of media. So depending on what devices you go through, the media access control will change, addressing possibly could change, and also the protocol you're using. So how do we construct a frame? We have a header, data, and trailer. And here's some of the sample fields. The ones where we're going to be concerned about is the start, the source destination address, the flow and congestion control. So we have a start, address, length, data, and trailer. So it's a specific bit sequence. So you have a destination source MAC address. You have your length. So the addressing is the NIC or the MAC address or the physical address. It is burned into your NIC card, so it can't be changed, although hackers will spoof it. We know that, but your NIC card is ingrained on a chip, and it will not change unless you use something like a software to change it. So if it's point-to-point, whether it's a logical multi-access, it's going to be governed differently. So you'll define the addressing that needs to move the network through the either local or the WAN. So we have remember, data link has a LAN component, and a data link has also a WAN component. So the role of the trailer is to check for any errors. It's error detection, not correction. So we'll talk more about this later, but basically it looks at the frame, does some type of a mathematical calculation, and determines if the frame's been damaged. If it's not been damaged, it goes through. And then the very last part of it's the stop bits, which is another bit pattern that will tell the frame that it's ended, and the next frame will be able to start. So wireless frame, so that's the collision detection multi-access collision avoidance. Now it goes to a serial point-to-point, changes the protocol to point-to-point, possibly changes the addressing. Now it's going to change to another WAN protocol, HDLC, so it's going to convert the frame into what it needs to for addressing in the protocols. Once again, it goes into the frame relay cloud. It will do its own addressing and also change the protocol to run across that. And now back to Ethernet, which is the carrier-sensing multi-access collision detection method. Goes into the frame and then to the PC, which stays also with Ethernet protocol. If we look at the total size of an Ethernet frame, we see that if we add all those up, it's going to be 1526. And so the important fields we're going to look at here is the destination source address and the frame check sequence. Those are very important to make sure the frame is complete. This is the point-to-point. So let's roll back one slide, look at the Ethernet, look at the format. You have the different fields. Look at the point-to-point, the fields are different because at the WAN component, the data link has to do something different. So that's why the encapsulated frame looks different. And then we can look at the wireless frame. It looks very, very different, and you'll get much more of this in later in your networking and your wireless classes. But just again, go back. They all look slightly different. So there's your Ethernet versus your point-to-point versus your wireless encapsulated frame. That'll conclude our PowerPoint.